poster presenters. First one is Alfaiz and Atif Hasan. It's a group from Aligarh Muslim, STS School, Aligarh Muslim University. And Salman from STS Aligarh Muslim University will be chairing this session. So Alfaz is a 12th grade student studying in Syed Hamid Senior Secondary School, Aligarh Muslim University, Aligarh, India. He is enthusiastic and self-motivated student by nature. He achieved various accomplishments throughout his studies in every arena, from academics to leadership. His hobbies include traveling and writing literature, and he aspires to become a medical student soon. With him is Atif Hasan, is an 11th grade student studying in Syed Hamid Senior Secondary School, Aligarh Muslim University, Aligarh, India, with major subjects in physics, chemistry, and biology. He got around 89% marks in class 12. He was the head boy of the school. He was volunteer in many school activities, NSS. He won many prizes in various competitions in school debates, extempore. He has won many times in essay quizzes. His hobbies are general awareness, swimming, public speaking, and he also aspires to become a doctor in future.
Well, thank you, Abid sir, for the introduction. Assalamu alaikum. Good morning to all the respected scholars before and beyond the screen. I'm Alfaiz, and along with my teammate Atif Hassan, today we are presenting a research project titled Cerium Doping Driven Electronic Modulation in Gadolinium Oxide for Visible Light Photocatalysis. This project was fully supported by the American Society of Science, Engineering, Technology, or ASIT, and was carried out under the guidance of Dr. Azra Parveen and Muhammad Zad from the Department of Applied Physics, Aligarh Muslim University. The basic structure of the basic aim or hypothesis was the project was to discuss these three major interconnected problems of the world. The first is environmental pollution, second is energy sustainability, and the third is the growing need for advanced functional materials. So one of the most serious challenges is water pollution. Industries release dyes, chemicals, and toxic compounds into water bodies, making it clean water inaccessible to millions of people. At the same time, we waste a huge amount of solar energy, which reaches us freely every day. Basically, what we are doing is we are not using the solar energy efficiently. Now, here are the contents of the whole presentation. Now, when we see in the recent decades, nanoscale synthesis of materials have become a central focus in the academic world as well as the industrial world. Nanoparticles are being used in all possible fields like biomedical, industrial, or agriculture. Here we present our research which involves the synthesis of gadolinium oxide nanoparticles, and we dope it with cerium. The doping with cerium occurs with the process of sol-gel synthesis, or we can say Pecchini process. Doping has been done in order to enhance the previously known or previously established properties of normal gadolinium oxide nanoparticles. So what doping does, doping with cerium seems promising because it has been shown to affect the structural, catalytic, magnetic, and luminescent properties of the substance.
Basically, gadolinium oxide is a rare earth metal oxide with high thermal stability and wide band gap, and also strong optical and magnetic properties. It has a cubic crystal structure and is widely used in catalysis, phosphorus, sensors, and biomedical imaging. Its ability to form oxygen vacancy rich nanostructures makes it attractive for energy and photonic applications.
So our basic aim was to utilize the waste solar energy for the purification of water. Also, what we did in this project was to synthesize the CE-doped gadolinium oxide nanoparticles. We also did perform some characterization, some professional characterization techniques in order to study the structural, optical, magnetic, and various other properties of the substance. And at last, we did find some potential applications of our substance. So here are some characterization techniques. like X-ray diffraction is there, scanning electron microscopy, and ultraviolet visible spectroscopy. They all are done in order to study the structural, morphological, electronic, magnetic, optical, and photocatalytic properties of the substance. Now, moving on to a very crucial part of the whole, that is the synthesis of the nanoparticles. So, so basically, gadolinium oxide and cerium doped gadolinium oxide nanoparticles were synthesized via Sol gel or Pechini process with utilization of gadolinium nitrate hexahydrate and cerium nitrate hexahydrate as the precursors. The gadolinium, briefly speaking, gadolinium nitrate hexahydrate was dissolved in ethylene glycol, and separately NaOH or sodium hydroxide was also dissolved in ethylene glycol, and they both were stirred at appropriate temperature and appropriate temperature. Subsequently, an NaOH solution was slowly added to the precursor solution in order to maintain pH, an optimal pH of 10. The solution was then heated at 110 degrees Celsius for 1 hour and further stirred at room temperature for 1 hour. The resulting solution undergoes the cleansing process by vortexing the whole product and in ethanol for like 2,500 rotations per minute for 6 minutes, and the whole process was then done twice and thrice in order to get a final precipitated white product, which was then calcified in an oven for 60 degrees Celsius for 24 hours, and the resultant gadolinium hydroxide pellets were then crushed into powder by using a crucible and further annealed at various temperatures, that is 500 degrees Celsius to 1100 degrees Celsius for 3 years, yielding the final and very final product, gadolinium oxide nanoparticles. So here is the data for X-ray diffraction. So what X-ray diffraction data tells us that our substance has retained a pure cubic phase even after the cerium doping. Also, it has been shown that the crystallite size has been increased, which basically means that the reactivity or the photocatalytic activity of the whole substance has been shown to be increased. Also, using the Scherrer formula on the top right of the page, we calculated that doping increases the crystallite size, which is beneficial because smaller particles mean more active surface area.
So basically, this is the data for transmission electron microscopy, which shows that our particle has a shape of pseudospherical, like it has a pseudospherical shape, and the average size of pure gadolinium oxide is basically 41.58 nanometer. This is the data for pure gadolinium oxide. So this is a slide for 8% cerium doped gadolinium oxide. Again, the size is pseudospherical. The size has not been changed. But again, the shape has not been changed. It is again pseudospherical, but the size has been reduced. Now the cerium doped gadolinium oxide has the size of 28.288 nanometer. Basically, this is the data for scanning electron microscopy. Again, it shows that our compound has the shape same as shown in transmission electron microscopy, but the holes inside these compound shows the porosity, which can help in the photocatalytic activity. This is the data for X-ray photoelectron spectroscopy, which confirms that the gadolinium oxide has +3 oxidation state at 531 electron volt, and the oxygen has the oxidation state at 532 electron volt. This is the slide for cerium doped gadolinium oxide, which confirms that our cerium has mixed oxidation state, +3 and +4, and it shows the peaks has been showed at different electron volts from 874 electron volt to 916 electron volt.
So here's the data for Fourier transform infrared spectroscopy, and that basically tells us that cerium has been successfully substituted in the whole substance. Well, the data shows strong metal oxide vibrations, confirming the successful cerium distribution into the gadolinium oxide lattice. As you can see at the 470 per centimeter wave number, we have been seeing cerium oxide and gadolinium oxide bonds. So this is basically a check that the whole process was done in an ethical and in a very uh, pure manner, and no mis errors were found till this phase. Atif, it's
Basically, this is the data for ultraviolet visible spectroscopy. It shows that the pure gadolinium oxide has the band gap energy 5.4 electron volt, but as we increase the concentration of cerium into it, the band gap energy has been decreased up to 3 from 5.3 electron volt to 3.5 electron volt. For the pure for the 8% cerium dope, the band gap energy is 3.5. Like it has been reduced from 5.4 to 4 to 3.5.
okay. Moving on to BET or Brenner-Emmett-Teller method. This basically shows us that the pore volume has been shown to be decreased with to be increased with the um, uh, doping of the cerium, and surface area has been increased, which basically means that the substance has become more reactive and more photocatalytic, uh, which will be helpful enough in proving our final hypothesis. So here's the data for VSM, or vibrating simple sample magnetometer. This shows that cerium doping has reduced magnetization and tuned the whole substance from weak paramagnetic behavior to strong paramagnetic behavior, and it has opened further more avenues in different fields, different areas like spintronic applications, and there are biomedical navigation applications of this. There are also photocatalytic applications of this, and many further applications. Moving on to the very most important result of the whole uh, project, that is photocatalysis. Cerium doping has significantly increased the photocatalytic property. As you can see, the 8% cerium doped gadolinium oxide nanoparticles have shown to have been shown to have been seen to get a 74% peak absorption of water pollutants. So now I'll briefly explain how photocatalysis works in our system. So when sunlight falls on our cerium-doped gadolinium oxide nanoparticles, the materials absorb this light energy. Because of this, electrons get excited and move from the valence band to the conduction band, leaving behind positive holes and carrying the negative charge towards the conduction band. So cerium doping plays an important role here as it reduces this band gap. It helps in better separation of these electrons and holes and reduces their recombination, which also increases the efficiency. The excited electrons react with oxygen to form superoxide radicals, which are basically a byproduct of this whole reaction, while the holes react with water to produce hydroxyl radicals. These radicals are highly reactive and they attack the methylene blue dye molecules that we tested and break them down into simple harmless products like CO2 or H2O. As shown in the graphs, undoped gadolinium oxide shows lower degradation, whereas cerium doped gadolinium oxide achieves up to 74% degradation under sunlight, proving its enhanced photocatalytic performance. And in the right side of the slide, you can see the image of uh, blue methylene dye polluted water turning to light, very transparent and crystalline pure water. So to conclude, cerium doping transforms gadolinium oxide from an insulator towards semiconducting behavior. Also, it increases the crystallite size and increases the surface area. Also, it improves visible light absorption and photocatalytic efficiency, and it tunes magnetic properties for multifunctional applications. Basically, what it does, it tunes the our substance into strong paramagnetic state from weak paramagnetic, which has further many high level applications like as we have discussed, biomedical and other applications. So here are the references that we've used for looking at the paper. Also for the acknowledgement. Finally, we would like to sincerely thank American Society of Science, Engineering, and Technology for funding this whole project. Also, we are very thankful to Department of Applied Physics, Aligarh Muslim University for technical facilities and resources. Special thanks goes to Dr. Azra Parveen and Muhammad Zad for their guidance and constant support. Also, we are very thankful to Student Support Group for Education, SSG, AMU Aligarh, for their mentorship. And again, special thanks to Dr. Sadia Ayub, ma'am, for her constant support. Thank you, and we will be happy to answer any more questions. Any questions?
Thank you, Alfaz. Now the session is open for any questions you have, any questions or queries you have.
Alfaiz, this is Muhammad Imam, but very good approach, and I do appreciate your effort.
A really big thank you to you, sir.
Thank you so much, sir.
First of all, I would like to say that Alfaiz and Atif, your presentation was wonderful, and you did a really great job. And I want to ask that why did you heat the solution at 80 degrees Celsius for so many hours? And why not you heat it faster at higher temperature?
Well, thank you, Daniel, for the great words. Actually, the temperature and the pH and the timing are all supposed to be optimal, because if we like do the process in higher temperature, the substance might get denatured or might turn into something unwanted. So we didn't want to do that, and we just followed the whole process that was established by the all the scientists and researchers who has gone past before us. Like in the reference, if you look, there is the first reference is actually the people who found this method of synthesizing these gadolinium oxide nanoparticles.
Thank you, Alfaiz.